Hello, this is a video about why learning how to do root locus is almost a waste of time, but I have a better way. First, I want to start with an open loop system. This was an example I found on the internet in another video. The open loop system has 3 poles at -1, -2, and -3, and a simple gain, and I'm going to call it a proportional gain. In the other video they just called it a gain, and with that they wanted to find the breakaway point. So I'm going to calculate what the breakaway point is using symbolic methods, and the results are going to be much better, although they're going to be the same. So first I have the closed loop system. And you can see this is the basic formula for a closed loop system, where we have the controller in the plant plus over 1 plus the controller in the plant. And if I do the substitutions into this formula, I get this. And then if I simplify, this is the result, and the characteristic equation is here. And this is pretty much like what you get with the root locus method. But here's where we differ. What I want to do is have a desired characteristic equation. That's what my DCE is. That's desired characteristic equation, and there are going to be 3 poles. There are going to be 2 poles, or a complex pair, that are going to do the breakaway, and 1 pole, mu, is going to move to the left on the negative real axis in the S domain as the gain is increased. When I expand the desired characteristic equation, I get a polynomial with coefficients for each power of s, and what I need to do is equate the powers of s for the desired characteristic equation and the closed loop characteristic equation, so that I have 3 different equations with 3 different things to compute. So the first step is to equate 6 plus p with lambda squared times mu, and then equate 11 to this value and 6 to this. So I have 3 equations, 3 unknowns, and it's very easy to solve this by hand. But when you get to have more complicated expressions, you might want to use a computer algebra system like WX Maxima or Sage. Those are free. There is also ones that are very expensive, like Mathematica, Maple, and MathCAD, which is what I'm using. When I solve for the gain, the lambda, and the mu, then I get 2 solutions. But since the gain is negative here, then only this solution is valid. So there's a gain of 0.3849, lambda is equal to 1.4226, and mu is equal to 3.155 at the breakaway point. This is very easy to compute. Now, let me explain what my complaint is about the root locus. The problem is there's only 1 gain, and the gain will never have the closed loop gain will never be 1. So it's not useful in this case to calculate where the poles are going to be if the response is going to be bad. So it really is a waste of time. Sure, you can go through the exercise, but it is a waste of time. In the YouTube video that I saw, there was also an example where, okay, so now what we're going to do is plot the solution, and I have a reference point, which is going to be at 1, and then this is the closed loop transfer function, and you can see that MathCAD does not solve the cannot do the inverse Laplace transform because the characteristic equation is not in terms of poles. MathCAD does much better if the transfer function is expressed in terms of poles and zeros. So what I did is I substituted the desired characteristic equation for the actual characteristic equation because they are equal, and using the formulas from above or values from above, I calculate a response, and you can see that if the set point was set at 1, the actual response would not ever reach the desired set point. So we've done all this work, and it's on a system that's not usable. So why bother? The Ethernet example, or the internet example that I saw, also wanted to compute the gain where the two complex poles cross the j omega axis. And I'm going to use the same technique to do those calculations. And it's fairly simple. I have my two imaginary poles, complex poles, and one real pole, and I get a desired characteristic equation. I then set the coefficients for the power s to the 0 power, s to the first power, s to the second power. So you can see that I got 6 plus kp is equal to omega times lambda. The 11 is equal to omega squared, and 6 is equal to a lambda. This is very easy to calculate by hand, and you get the solution 60. The frequency is going to be 3.3 radians per second. That's going to be plus or minus. You see there's two solutions. And the real pole is going to be at 6 radians, or negative 6 radians, when the gain is 60 and the two complex poles are on the imaginary axis. So let's plot that out. So again, I'm using the desired characteristic equation in the denominator, and I can do the inverse Laplace transform. So this is the equation, and you can see that again I have a set point of 1, but the response is not usable. So again, more wasted time. Now, just to show the power of using symbolic calculations, I am going to solve for the 3 roots, the 3 poles, symbolically, and I get this long solution. Let's see if I can show you some of it. Oops, too much. Very big. And what I'm going to do is simplify that. So there's this term here that I'm going to assign it to a temporary variable called q, and then substitute q in wherever that term is being used. So now I have a symbolic formulas for all 3 poles, A, B, and C, and I'm going to iterate kp from 0 to 80 in steps of 1,000ths. That way the curve looks smooth. So when I do that, I get a nice plot. You can see this is the A root pole. You can see it starts out at -1, moves this way. The B pole moves. This is the breakaway point. And then this is the C pole, and it starts at -3 and moves off to negative infinity. But the key points here is this is the breakaway point at minus 1.4226, and then this is where the gain happens to be equal to 60. So far, the root locus has proven to be useless because we can never use that for a real closed loop system. So let's try using a PID. And we'll find that even a PID has problems. So let's start with the original open loop plant. There's 3 real poles, and it's a non-integrating system. And because of that, we need to have an integrator. And the integrator will make it so that the process variable will reach the set point, or the target will reach the actual, however you wish to express that. So this is the PID. And again, we have the closed loop transfer function. I'm going to simplify it so I have a characteristic equation. And now I need to have a desired characteristic equation. And we can't place all the poles on the negative real axis because we don't have 4 gains. But we can have 2 poles on the negative real axis, and then we can have 2 or a complex pair of poles that we can place. So we have 4 poles, 2 real poles, and then 2 complex poles. And if I expand that out, I get an equation that stretches out across the page here. But my technique for placing these poles is going to be the same as what I did above. I'm going to equate the coefficients for each power of s. So I have ki is equal to the lambda squared times mu times nu squared. That's this. And you can see that ki is the characteristic equation here. And then I have kp plus 6 is equal to this term. And kd plus 11 is equal to this. And there's no gain for the for 6 is equal to well, this coefficient. So the fact that we don't have a gain here limits us quite a bit. When we solve for ki, kp, kd, and lambda, remember we got 4 equations, so we have to have 4 unknowns. So we make lambda an unknown. This is the solution that we get. Now, this is going to be a little bit more difficult to solve by hand, so you probably want to use a computer algebra system for this. The significant part is the lambda is equal to 3 minus mu. And this is very limiting. What that means is that no matter what we do with the gains, we can only place the poles where the real parts are going to be between 0 and -3. And that limits how fast the response can approach the set point. If we make mu 1, lambda can be equal to -2, or it will be equal to 2, so the pole will be at -2. If we make mu a 2, the lambda will be a 1, so the pole will be at a -1. But that pole is not very far to the left, so the response is going to be very slow because you're going to have terms like e to the minus t or e to the minus 2t. The response, again, is going to be very slow. Now, mu and nu cannot be calculated. They kind of float until you assign values to them. And the equations, you can see, get to be fairly complicated unless you assign them values that, well, if you can assign values in terms of lambda, then that simplifies things quite a bit. And what I'm going to do is I'm going to assign mu and nu to 1.5. And because mu and nu are the real parts and the complex parts of the complex, or imaginary parts of the complex pole, the damping factor will be 0.707. And the lambda and the mu will both be at negative, well, they'll both be at 1.5, so the poles will be at -1.5. And that should optimize the response. So here are the calculations. And you can see that when I place mu at 1.5, lambda is at 1.5. And these are the gains for Ki, Kp, and Kd. So let's plot the response. So this is the closed loop transfer function with our set point. I'm going to do the inverse Laplace transforms. Again, that kind of stretches across a couple of pages. I'm going to simplify it, and this is what I get. And the response looks like this. And you can see that the response is much quicker here than what we had above, where we just had one gain. The other thing that's significant is that the integrator allows us to get to the set point. There's only one problem with this, and that is, or actually two. One is that we can't make this response any faster, and the second is that it overshoots. So a poor control person out in the field that is saddled with a machine like this, there's nothing that he can really do to tune it up to make it go any faster. He is limited by the open loop poles of the system. So let's try a different technique. Let's try adding another gain. We're going to add a second derivative gain. We're going to use the same technique as above. So here is our open loop plant again. This is our controller, and notice it's a PID with a second derivative gain. This is the closed loop transfer function, and this is the characteristic equation. But notice the second derivative gain is now a part of the coefficient for the s to the third power, and that allows us to place all four poles. What it allows us to do is place all four poles on the negative real axis, so there's no overshoot, and we can also move the four poles to wherever we want along the negative real axis. We also find out that the calculations are very simple. So equating the four poles again, let's just go up here. You can see that I got Ki is equal to lambda to the fourth power, and Kp plus 6 is equal to 4 times lambda to the third power, and so on. Do the calculations, and we have now Ki, Kp, Kd, and K2 calculated out symbolically. And I'm just going to assign lambda to 10. So now we have four poles at minus 10. And that is much farther to the left than what we had before. Remember, with only one gain, we could have one pole, or the two poles at minus 1.4. And then adding a PID only allowed us to move the poles, the real part of the poles, to minus 1.5, but now we can move them to minus 10, or even higher if we want. But there are physical limitations to increasing the gains too much. But first I'm going to calculate out the response. So I'm going to do the same inverse Laplace transform. And here is the result and the numeric solution. And you can see that the response is going to be much faster. The reason why is because the poles are moved farther to the left. And this is due to the fact that we have one gain for every pole. You've got to remember that the integrator brings along its own pole, so the integrator doesn't really help add gains because it has its own pole. But what the integrator does do is it allows us to reach the set point. So you can see that there's a little bit of overshoot here, and you would expect with four poles it would act like a low-pass filter. But because we used a PID, we have zeros. And the zeros will cause overshoot too, just like, well, not just like, but it will cause overshoot. And you got to be careful about where the zeros happen to be. And as it turns out, if you look here, if you look as time goes to zero, or time goes to an infinity, this term will eventually go to zero. But in the meantime, what ends up happening is that these terms end up being positive, and they cause the output to be higher, this part here to be positive for a while, and that added onto this 1 will make it so that there's an overshoot momentarily until t gets big enough where this whole term gets attenuated. So let's remove the Kp, Kd, and K2 gains from the forward path. Now, in temperature systems and many other types of systems, you have the option of having the derivative gain act only on the change in the process variable or the feedback. And actually, it's advantageous to have the gains other than the Ki gain. It's advantageous to have the P gains and the D gain and the second derivative gain all work on the feedback or the process variable. And what that does is it removes the zeros. And by removing the zeros, you can see that I've removed the K, P, and the KD and the second derivative gain. I end up getting a response that very cleanly moves up to our set point and stops without any overshoot. Now, the gains that are calculated are identical because the poles are in the same place. Now, something you should see here is I can move these poles wherever I want to along the negative real axis. And as I move them closer to the origin, you can see the response gets to be slower and slower. And then as I move them away from the origin, the response gets faster. Move it back here, that's the default. So this allows us to get the kind of response that we want. And then other things that you should be aware of is that we could move these poles around so that we can get a Butterworth type of response, Chebyshev response, just about any kind of filter, 4-pole filter that you can think of. But for motion control and for most control systems, you want to have a critically damped response where you move up to the set point and don't overshoot. Now, let's look at the Bode plot for this. This is the Bode plot for the using the PID with the second derivative gain in the forward path. So here you can see this is the controllers, and here, and this is the system, open loop system, and this is the closed loop transfer function. I'm doing the calculations, and the bandwidth is 7.04. And you can see the response. The blue is the phase, and it goes down to -90 at the higher frequencies. It won't go any lower than that because we have 4 poles and we have 3 zeros. The 3 zeros are going to add phase lead, the 4 poles add phase lag, and so the difference is 90 degrees because there's 90 degrees per pole. The part that causes the overshoot is this part right here. So whenever you have zeros, usually there will be a place at a frequency range where the response is greater than 1. And because of that, you have an overshoot. But you can see that the bandwidth is expanded or is higher than what we have down below. So let's go down below where we have only the integrator in the forward path. Now there are no zeros. You can see that the bandwidth is much lower and the phase delay is going to be much higher, but there will be no overshoot. And the response, you can see, is much slower in the graphs up above. So the point is, there really isn't a point to learning how to do the root locus. Just knowing that a system is stable is not good enough. If you're doing motion control, any kind of plant control, you need to have the closed loop system reach the set point in a reasonable amount of time. And being off and oscillating is just not acceptable. So you really need to be able to do calculations where you can use more than one gain, like what we can do here with the symbolic calculations. This is basically called pole placement. And that gives you the freedom to place the poles and get the desired results. So, one more comment. I'm going to go back to the beginning. All of this is useless. What you really need to know is, where does this information come from? If you don't have the open loop system, root locus, pole placement, it's all useless. So whenever you see the instructor, ask them where the open loop transfer functions come from. I'll cover that later. Bye.